Let's start by exploring visual feedback, a fundamental aspect of user feedback in the metaverse. Visual feedback refers to how graphical elements are displayed in response to the user's brain signals or motor actions. For instance, imagine virtual hands that move in sync with the user's motor imagery. This kind of feedback greatly enhances the user's sense of presence and agency, making them feel in control of the virtual environment. However, there are challenges. Prolonged visual feedback can lead to fatigue or confusion if it's not precise or consistent. Therefore, design considerations for visual feedback must prioritize user preferences, cognitive load, and expectations to ensure an immersive and comfortable experience. Moving on to auditory feedback, which introduces another dimension to the BCI experience. Auditory feedback leverages sound to enhance the integration of BCIs with the metaverse, adding layers of spatial and emotional context. For example, auditory cues can provide users with spatial awareness or emotional cues that enrich their immersion. The advantages include better information transmission and reduced cognitive load, as auditory signals are often processed more intuitively by users. However, developers must carefully design these feedback signals to avoid sensory overload and assess how sound impacts the user's brain activity. Common applications of auditory feedback include entertainment, communication, and even therapeutic contexts. Haptic feedback, which involves touch, vibration, and temperature, is crucial for enhancing the realism of virtual experiences. In VR and AR environments, haptic feedback improves usability by providing a tangible sense of presence. For example, when interacting with virtual objects, users might feel a simulated texture or resistance. This feedback helps users engage more deeply and intuitively. The primary challenge here is designing comfortable haptic devices that can deliver consistent, diverse sensations across different body locations. Haptic feedback holds great promise, particularly for learning and rehabilitation, as it engages users' sensorimotor loops, promoting neural plasticity. Robotic feedback adds another layer of complexity, as it involves informing users about a robot's actions when controlled through BCI. This feedback is essential in contexts where users remotely control robotic devices in real time, such as in telepresence or rehabilitation. It provides users with a sense of the robot's state and actions, helping them feel more connected and in control. However, challenges include maintaining data privacy, ensuring security, and adapting the robot's behavior based on the user's cognitive and emotional states. Applications range from education to entertainment, where robotic feedback can make human-robot interactions more interactive and meaningful. Olfactory feedback is a unique and emerging aspect in BCI applications, providing scent information in virtual environments. Imagine a scenario where the metaverse can simulate various scents, enhancing the user's experience by aligning it with visual and auditory feedback. Olfactory feedback is advantageous because it can deepen immersion and engagement, particularly in scenarios where scent evokes memory or emotional responses. However, creating realistic olfactory stimuli is complex, and accurately measuring user satisfaction and brain response remains a challenge. This type of feedback has potential applications in fields like learning, memory, and even emotional regulation. Mental feedback utilizes direct brain signals to guide interactions in the metaverse. This feedback can be implicit, where the environment adapts to the user's cognitive or emotional state, or explicit, where users can control elements in the environment with their thoughts. For instance, an implicit response might involve adjusting brightness if the user is fatigued, while an explicit response could allow a user to move an object simply by focusing on it. Mental feedback increases personalization and interactivity, but it also brings challenges regarding reliability, privacy, and security. Handling brain data ethically and ensuring usability are crucial to making mental feedback effective in the metaverse. Now, let's look at the overall landscape of immersive user feedback in BCI. This slide presents a distribution of different types of feedback used in BCI applications, as illustrated by a pie chart. Visual feedback is the most common, making up 44% of the research focus, followed by robotic and auditory feedback, each at 23%. And haptic feedback at 10%. The trends from 2017 to 2022 show a steady increase in the focus on immersive feedback, with visual feedback exhibiting the highest growth rate. This trend underscores the growing recognition of how crucial feedback modalities are in creating a truly immersive metaverse. Finally, This slide delves into the analysis of BCI user feedback across different immersive environments, including VR, AR, mixed reality, XR, digital twins, and haptic technologies. For example, visual feedback is particularly prominent in digital twins, 43%, and XR, 50%, while haptic feedback is central in the haptic technology category, 38%. Meanwhile, VR, AR, and mixed reality applications show a balanced use of visual and auditory feedback. This analysis provides insights into how researchers are allocating attention to different feedback types within specific environments, highlighting the varied approaches in achieving immersive experiences across fields. Ultimately, this informs our understanding of where feedback mechanisms are most impactful and where further exploration is needed.